Welcome to our first unit in Module 4, Science and Decision Making. And in this unit, we're going to look specifically at argumentation in science education. So you're probably wondering what on earth argumentation has to do with science lessons. And so in this particular unit, we're going to unpack that a little bit so that you can get some clarity on that. So the inclusion of this novel approach is emerging in science classrooms around the world. As a recent science education research suggests, it's an effective strategy for providing school students with a better insight into the nature of scientific inquiry and the ways in which scientists work. Unfortunately, what tends to happen in school science is that teachers rush from topic to topic, and students are too often asked to accept many ideas without the opportunity to consider why they are believed to be true. And we know this particularly when students get to the junior secondary years, because we tend to rely very heavily on textbooks in junior secondary, which is a big shift actually from primary school. And all of a sudden, students are expected to be able to read and understand all these ideas that are presented in texts, and the way that texts present ideas is very much in a fact-based manner. So, that sort of tentative nature of science tends to be completely ignored. So much of the evidential base for belief in standard scientific ideas is neither simple nor straightforward. The major cultural achievement of science has been to establish a body of hard-won knowledge, transforming our vision and understanding of the world around us. And we've had some exposure to that. It's particularly when we looked at the history of science, and we can see that there is no way that science is straightforward, and that a lot of the time, dominant scientific ideas that we have now had to be fought for by scientists. So this has been done by constructing arguments from a body of data and observations that support innovative and creative theories about how the natural world behaves. Yet the evidence and arguments for scientific beliefs are often underexplored in school science. We just tend to show the evidence at the end. We don't show the process through which that evidence became accepted. So what does this term argument mean in science? And why is it a significant feature of science? So you can see up the top here, most people's everyday sort of belief about what an argument is someone's right and someone's wrong. Whereas we want to sort of propagate a different view of what an argument is in science. So the everyday meaning of the word is not the one that's being used in the science classroom. So think about your own interpretation of how you would define argument, and consider what the term might mean in the context of science. That's a really important question to ask. So what's an argument in science? There's different kinds of arguments we can have. So there are arguments about what kind and the amount of data to collect. For instance, whether the data will be valid and how much is needed to make it reliable. So that comes back to some of these things we talked about how many trials did a scientist do? How many times did he conduct an experiment, he or she, and repeat that exact same procedure each time? Because a lot of the time with experimental science in particular, the ability to replicate and to have a number of trials is sort of an important hallmark. A second kind of argument, there are arguments about whether a given model is a satisfactory interpretation of the data. For instance, why the Bohr model of the atom is no longer a satisfactory model. So now we have a revised model of the atom that we teach. A lot of the time it's based on a quantum view of the model, but all the different models that have come before it have helped inform the model that we use now. So there's arguments about, well, which is the best model to use? Which is the most effective for teaching the ideas? There are also arguments about the interpretation of data, and these are probably the most common ones. So, for instance, do the rising levels of CO2 mean that global temperatures will rise? That's a very key argument linked to global warming. And as you know, and you've seen this one in the media, this is widely debated. Okay, so we can look at what we're collecting and how much we need. We can look at the models we're using as a basis of interpreting our evidence, and then we can look at interpreting data that leads to theories. So all different kinds of arguments. So argument can be thought of as a central component of science. We just don't tend to see this process. We just see the conclusion of it. We see what's written in our textbooks. We don't see how the evidence came into being. As such, we need to have some sense of what the components of argument are. So to begin with, we're going to try and identify evidence that supports or refutes a claim. So you either support it. When we say refute, we mean that it disagrees with it or it has a counter to it. So we're going to have a look at activity on the following slide, and we're going to look at two competing theories. So remember, a theory is a large set of empirical evidence supported by a number of claims and assertions by scientists to try and understand a phenomenon. Okay, so a lot of the time in science, we have different theories for the same concept. So one of these, theory one, is a common misconception, and the other one, theory two, is the currently accepted scientific view. So there's two different ones we're going to look at. Beneath each theory are some pieces of evidence. Now, this evidence may support one of the theories, both of the theories, or neither theory. Okay, so we can have a set of evidence, but we can look at how that evidence is used to support theories. Okay, so we're going to have a look and decide whether the evidence supports both theories, one theory, or neither theory. So let's have a look. Here's our first theory. Light rays travel from our eyes onto objects and enable us to see them. All right, so in the primary school setting, we do look at light energy when our students are in primary school. So this is something that as a teacher you may have to actually teach. The second theory is light rays are produced by a source of light and reflect off objects into our eyes so we can see them. So one of them is a misconception. It's not supported scientifically. Excuse me. And the other is the scientifically accepted view. So you need to have a look at the evidence. So don't just go, oh, well, it's this one or that one. Have a look at the evidence. So this is what scientists do. They look at the evidence and they look at how the evidence can support or refute a theory, and then they make a judgment. Okay, so let's look at the first one here. Light travels in straight lines. All right. So which one does that support? Theory one or theory two? So it could support both if you have a look at it. Light rays travel from our eyes onto the objects, so light can travel in a straight line there. Light rays are produced by a source of light and reflect off. So that one, although it's a valid piece of evidence, it doesn't help us decide, does it? What about the second one? We can still see at night when there is no sun. Does that support both or refute both? Okay, it actually supports both. Like, we can't make a decision based on that piece of evidence. The third one, sunglasses are worn to protect our eyes. Now, this is an interesting one because this piece of evidence is not relevant in any way to this argument. So actually, it's not applicable. So we can kind of dismiss that because as a piece of evidence, it's not very effective at all, and it does nothing to help us support or refute either theory. The fourth one, if there is no light, we cannot see a thing. So if there's a complete absence of light, we cannot see a thing. So let's look at theory one. Light rays travel from our eyes onto the objects and enable us to see them. So if light comes from our eyes, that's how we see things, then that piece of evidence number 4 cannot support theory one. It can only support theory two. Light rays are produced by a source of light. So that means that it's not our eyes that's the source, it's something else, such as the sun or a light bulb. Okay, so if there's no light coming from a light bulb, we can't see anything, can we? So that one actually supports theory two. Number 5, we stare daggers. We stare at people, we look daggers, and we catch people's eye. Again, this is similar to point 3. It's not applicable to this argument. So often, and you'll see this in the media quite a bit, sometimes evidence is put forward to support different theories, and it actually is not applicable at all to the theory under question. So 3 and 5 are really just a waste of time. 4 is valid scientific evidence, and it can only support theory 2. Okay, so theory 2 is the one. And here, this little diagram at the bottom gives you some understanding. So here's our light source. Light travels in straight lines from the sun. It's reflected off an object, and then those light rays are received in our eye, and that's how we see. It's not the other way, where the arrow goes this way and where the light source. So we'd kind of like have a torch behind our eye. That's not how it works. So thinking back there, reflect on the difficulties of using this kind of exercise in the classroom. Now, lots of teachers worry about teaching misconceptions, or they worry about using them because they worry that it might reinforce the incorrect view, But as we know, and you've done some constructivism, I know in your degrees, that the research shows that opportunities to consider common misconceptions as well as the scientific conception leads to a better understanding of the scientific conception. Because remember, we've got to get our students to challenge their pre-existing views, because many of them might have held that misconception. And in this way, we can challenge it and get them to see that the scientific view is the more useful one. Importantly, it would make sense at the end of an activity like this to hold a class discussion and evaluate the evidence critically to show that some pieces of evidence are more significant than others and that the bulk of the evidence supports the scientific view. So let's look at a model that we can use to sort of unpack the different features of an argument. So there was a philosopher called Stephen Toulmin, and we're going to use his model as a basis for characterising argumentation in science lessons. So our first step when we're analysing an argument is to try and work out which part of it is the claim, the substantive claim. And you're probably thinking, well, what's a claim? It's basically an assertion about what exists or what people think. So it's someone putting forward like, humans are causing global warming. Okay, that's a claim. Okay, we're claiming that humans are responsible. Okay, or humans are ruining the environment, or light rays travel from our eyes onto objects and that's how we see. That's a claim. Okay, so once this is established, the next step is to identify the information that's used to directly support the claim. This is defined as the data. Okay, so the data are statements that are used as evidence to support the assertion. Okay, so for instance, with the global warming one, if the claim is humans are causing global warming, the data could be there's been an increase in emissions of CO2 since industrialisation or something like that, and that's the link that supports the claim. A further elaboration of how the data is related to the claim is referred to as a warrant. And there's another piece called a backing, which is additional information that supports a warrant. So you're probably thinking, oh, that's too many terms. Well, we're going to go through and look at an example so you can see how those play out. Importantly though, elements of an argument that counter the data, warrants or backings are called rebuttals. Okay, so they're ones that go, well, no, actually that evidence does not support your argument. So argumentation can be thought of as a process of constructing a claim which is justified by data and warrants. It's a process which seeks to establish scientific concepts. So scientists use it all the time. So here we go. Here's some definitions. And this over here, this figure is really important. So here's our claim, and our data directly supports our claim. We can also have something called a qualifier, and this tells us the specific conditions under which the claim holds true. Okay, so we might have some data to support a claim, but the qualifier might be, but only when the temperature is 30 degrees, or it could be a particular condition that has to be met. All right, so we went through these: claims, data, warrants, qualifiers, backings, and rebuttals. So we're going to see how these play out in an example. So let's have a look at a couple of sets of arguments. You can see them there on the right. And we're going to look at the first one. It's an everyday example. It's not a scientific example, so it might be a bit easier for you to relate to. But you can analyse the following four in the same kind of way. So what is the claim? Let's go back. So Manchester United are a better football team than Arsenal. They have won more football matches at home and away because their players have superior skills. That's the argument. So which part of that is the claim? So the claim is the assertion. It's what we're saying is true. So it's easy with this one. It's the first sentence. Manchester United are a better football team than Arsenal. That's the claim. What about the data? Excuse me. What evidence supports that claim? Why are Manchester United a better football team? Well, you can see it right here. Because they've won more football matches. Okay? Okay, so what part is the warrant? So how do we connect that data to the claim? They've won more football matches at home and away. The warrant is here because their players have superior skills. So the reason they win more is their players have more superior skills. So that's the warrant. What might be a qualifier? What might be a condition? So one's not stated, but it could be implicit that, well, this is only in some years, because if we looked back maybe 40 years ago, that may not have been the case, because their players may not have had more superior skills. Is there a backing? Is there any assumptions, excuse me, that are often not made explicit? Not in this case. Can you think of a rebuttal? Oh, here's one here. Manchester United players only have superior ball skills. Arsenal are renowned for their team working skills. So that's a possible rebuttal. Again, it's not made explicit, but it's a possible counter, okay, to the evidence that's presented. So let's have a go at constructing a written argument. So writing offers a way of developing argument, conjecture, and challenge. And in writing, learners will articulate reasons for supporting particular claims and attempt to persuade or convince their audience. They will express doubts, ask questions, relate alternative views, and point out what is not known. So while spoken arguments demands all of these skills, writing an argument requires students to be more thoughtful about articulating these elements. So actually a written argument is quite a bit more challenging than a spoken or an oral argument, because it actually forces you to think really carefully about the different aspects before writing them down. However, the style of writing or the genre used in science and argument is often unfamiliar, so it must be supported. It's not the standard genre that we write in. We usually write scientific reports, and we tend to use very factual language, whereas writing an argument is a different style of writing. So let's have a look at this example. So there's a scenario here which we need to construct an argument to explain whether sound travels faster in water than in air. So here's the scenario. So you can see Michael sitting here in the boat and Nassim in a boat as well. So Michael's sitting in a boat on the ocean. The boat has a metal hull, so it's made of metal. He is hammering the bottom of the boat. So you see a hammer here. Now Nicola here is swimming underwater and Nassim is in a boat on the water. So will Nicola or Nassim hear the sound of the hammering first, or will they hear it at the same time? Okay, so you're going to construct an argument to support one or the other. So it's a bit like the two theories about light. We've got two different ideas. So one of our claims could be Nassim will hear the sound of hammering first because sound travels faster through air than through water. The alternate one could be, the other claim could be Nicola will hear the hammering first because sound travels faster in water than in air. And even a third argument could be Nicola and Nassim will hear the hammering at the same time, and why. Okay, so here's the evidence that we would give our students, all right, the scientific evidence to try and construct their argument. So they would see how each of these pieces of evidence supports a particular claim. So if you're interested, the scientific answer is that the water particles are much closer together than the air particles. So consequently, they are more likely to bump into each other than the air particles will. And the vibrations, because we know that sound travels via conduction, you might remember that from your science education classes, curriculum classes. So the vibrations will travel faster with the particles in the water because they're closer together and they'll pass that sound along, like a chain reaction. So Nicola will actually hear, if we go back, oops, I've gone forward. So Nicola will hear, our argument will be, Nicola will hear the sound of hammering first, and our evidence would be because sound travels faster in water than it does in air, and our backings and our warrants will be water is denser than air, sound travels by compression waves, it's much easier to compress air than it is to compress water. Actually, that's not relevant. Vibrating particles bump into each other, etc. Okay, so the evidence should be provided to the students, so don't just give them the argument. So what tends to happen is teachers give the students that. Now, if you can imagine, number one, that relies on students having some understanding of conduction. Number two, it relies on students being able to interpret that and understand what the question's asking. So it's too challenging. Even in junior secondary, that's too challenging. So they need to have more structure. So we provide the scenario and we provide the evidence. That's really key. Here's the evidence. Always provide the evidence, because if you don't provide the evidence, they're just going based on anything, their own private theories, which could be scientifically inaccurate. You may also want to incorporate the writing frame on the next slide. So my idea is, this is where they say Nicola will hear first or Nassim will hear first, the evidence to support my idea. So they look at that list of evidence and write down which evidence supports and why, arguments against my idea, and then I would convince someone who doesn't believe me by, and then they write that down. So that's really good. It gives them the structure. So here's one for you, just to finish off this mini unit. So we've got another scenario here, and we've got a set of evidence, and this one's for you to work out. So we have two snowmen. We have Fred, who's not wearing a coat, and we have Bert, who is wearing a coat. And Fred's claim is, I think I will melt first because the sun will hit me and the heat energy will change my snow into water. Okay, so that's one argument. Bert says, I think I will melt first because I would trap all the sun's energy inside my coat and this will cause my snow to melt into water. So that's Bert's argument. So you have to decide which argument you support, and you need to use this evidence to help you construct that argument. So here's your activity. Develop a scientific argument to support your claim about which snowman will melt first, Fred or Bert. Ensure you consider the additional evidence provided, and I'd love for you to share your argument on the discussion board to see what other students think as well.